What I'll talk about today, this is the first of a two-part series of videos where I'm going to be discussing some things about the physiology of skeletal muscles, a little bit about the physiology of exercise, as that relates to how it is, or why it is, that I have been saying online that the undertaking of aerobic type activities, those kind that are generally the lower intensity or moderate intensity, long duration exercise protocols, whereby there are rhythmic muscle contractions of the large muscle groups, for example, slow walking, moderate walking, jogging, cycling, those kind of activities that go on for hours at a time and at a relatively low sort of intensity. So I've been saying online that that's a bad idea to do that kind of stuff to your body. It's not good for your health, despite what we've been told for many years. And I'm going to be explaining what that is, starting with this video, which is the background information that you need to understand in order to get what I'm going to say in the second video, which I'll post later in the week. What I'd like to do by way of covering this information off is to refer to a review article that I wrote some years ago now in 2010, whereby I looked at one of the basic exercise modeling or exercise performance predictive tools that's been used for a while. And I used that to show how the idea about exercise physiology, about energetics of muscle contraction, some of those ideas that are being taught are not so good. A bit of idea that's being taught to exercise physiology students for many, many years. It's still being taught today. It's still wrong. And it says that there are three discrete energy systems, one of which is aerobic and two of which are anaerobic, those being the aerobic metabolism, the beta oxidation of fatty acids and indeed sugars and things like that, and thus producing ATP in the mitochondria. The second pathway, the second discrete pathway, is often referred to as anaerobic glycolysis or simply glycolysis, which is the splitting actually of glycogen, so that's glucose starch in the muscle fibers, directly at a substrate level, using oxygen and producing AT3. Hence, that's why they refer to it as an anaerobic energy pathway. On the third anaerobic energy pathway that they talk about is the phosphocreatine or PCR system, which basically is the splitting of phosphocreatine into two molecules, one of creatine and one of inorganic phosphate, thus releasing some chemical energy which is used to put together an ATP from an ADP plus an inorganic phosphate. So pretty much those are the three energy systems that they teach. There's actually even a fourth one, which is also so-called anaerobic, that a purine nucleotide exchange, which I won't get into today because it's a bit technical. About the level of this discussion, we'll get to that another day, perhaps. In any case, they're taught, students are taught there are three energy systems. One of them is aerobic, two of them are anaerobic, and as such, they're taught that we have both an aerobic capacity and an anaerobic capacity, and that these are independently trainable, and that the systems are one or the other, and one predominates over the other depending on the intensity and duration of exercise and being undertaken. There's a lot of technique that they use or have used, some people have used, called critical power. That's what this paper here is about. It's called Critical Power Revisited, an alternate interpretation of physiology based on observation. In other words, that theory that I've just outlined to you, that's the basic idea that's taught. Three energy systems, here they are, 1, 2, 3. One uses oxygen, the other two bind. But pretty much that's how it is. We have both an aerobic and an anaerobic means by which we can produce energy for muscle contracting. The problem with it is it's absolute nothing. Absolute none. This discussion, this video is about why that's so. So basically, we start off by introducing what it is that the CP modeling system is. What we see here at the top right-hand here is figure 1. The solid black curve here talks about the time to exhaustion versus the exercise intensity by way of either work output in the case of something like cycling or swimming or those kind of things, and the velocity of movement across the ground in the case of running for sports. And basically, what it boils down to is if you were to exercise to exhaustion, obviously the lower the relative intensity of that exercise, if it's a steady state intensity, the longer you can go for. So in other words, if you exercise at a very low relative intensity, you can keep that up for quite some time before you are exhausted and have to stop. As the intensity goes up, the duration of time that you can keep that exercise up for goes down. I don't think that's any surprise to anybody. I think that's pretty much anybody's experience of the human condition. That's how it goes. No shock there. And that graph just talks about how that is. And it's modeled as such as a curve, and that's pretty much just describing that. But so moving on a little bit. Now we're looking at a graph of it's a critical power graph here. Figure 2 there. What we've got here in the black solid line here is a straight line. That a straight line portion. And what that is that derived for any given individual, athlete, person, whatever it is, whether an athlete or a person, whatever it is, doesn't matter. What happens is we get that person into the lab on, perhaps 4 or 5 occasions so that we've got enough points to convince ourselves that our line is what it should be, a straight line. And we exercise those people from complete rest to complete utter abject exhaustion. They have to stop. They cannot exercise anymore. And we do that at 4 or 5 different exercise intensities, thus meaning that we cater them quicker or more slowly. We do those in random order. And then we plot those on the graphs. The actual data points are not shown on this graph because it's a hypothetical example, although they usually fit very, very closely to the straight line. The residuals are very, very small. It is a really good predictive measure. It worked really, really well. Generally, you get a very, very good straight line that you can draw through the points. And that's what you get there, that black thing there, the straight line. So the slope of the line here going from a low value on the left-hand side to a higher value on the right-hand side, that is thought or described by authors of the critical power assessment on as a figure of one's aerobic capacity. The steeper that line is, the better one's aerobic capacity is. And then down here, there's a y-intercept, which is a very similar, but non-zero value. Okay. And that y-intercept there is touted as being the anaerobic capacity of that individual. If you drew a straight line across there, you'd say everything under there is the anaerobic capacity of that individual, and everything in here is their aerobic capacity. And so this model is touted as being able to describe both aerobic and anaerobic capacities, both collectively and individually, and it's thought to be a very clever thing. But until you actually apply your brain and think about it, and problem number one that brings us over here immediately, this value here, this y-intercept value, suggests that this prediction, if you extrapolate backwards from about 60 seconds to no time at all, zero, this straight line predicts that you should be able to complete a small but an amount of work without spending any time to do that work. In other words, instantaneous production of energy, instantaneous production of work. Now, if you look at the physics of this, that's entirely impossible. That's ridiculous. That cannot occur. This prediction is wrong for exercise durations to exhaustion lower than about 60 seconds. In other words, every single repetition that you will probably do in a repeated set of high intensity resistance training, for example, I mean, how do you produce work in no time? Because work, is the time is in the sun there. You have to have some time to do work. You can't do something and not take any time to do it. It's impossible, is what I'm saying. So therefore, this prediction has its limitations. It is false if you extrapolate backward from about 60 seconds towards zero. And that's impossible. That can't occur. What that also means is there is no such thing as an anaerobic capacity. Interesting, isn't it? Because the anaerobic capacity is modeled as how much work you can do instantaneously. And the laws of physics, the law of physics tells us that it is zero. So there you go. That's impossible. So basically what I did, that's what this paper is about. Among other things, is I produced this correction, which is the dotted line here, which I'm just tracing now that you can see hopefully. That's the dotted curvilinear relationship between about a minute or so backwards towards zero. And what it does is it curves that straight line prediction from linear periods in that past minute. It curves it back down to zero to bring it into line with what is possible in terms of actual physics and actual phenomena in the actual universe. And how did I do that? I did that by going back to figure 1 here, and I put in a time constant, which is a lag time in between the oxygen uptake at a given steady state of exercise. On you make a step change in exercise intensity from one level to the next level up, whatever that is. It takes an amount of time for your oxidative pathway to catch up. Why is that? It's because the oxidative pathway has inertia. Inertia is the resistance of a body to a change in momentum. And that's usually thought of in terms of a physical body, like a train, a plane, an automobile, a rock in space, a planet, or whatever it is that's moving. It takes a lot of energy to change its state of motion, and its resistance to that change in motion is inertia. In the metabolic systems, the inertia that we're talking about in the aerobic system, it's in the system where mitochondria consume oxygen and produce energy for us. When we undergo a step change in exercise intensity from one level to the next, it takes time to catch up. There is a lot of inertia there. And so that's why that is. So I put that time in there, and that gives us the curvilinear nature of that line, and that brings it back to a, physically, phenomenologically, scientifically a possible prediction. And it predicts correctly that in no time whatsoever, in zero time, the amount of work that you can possibly achieve is indeed correctly now stated as none. And it also discounts the possibility of there being a separate, discrete anaerobic system that operates without reference to oxygen. Interesting, isn't it? So that's basically how that is. How does that work in the world of physiology? What's the mechanism behind this theory? Well, here it is here on this figure here at the top of the page 70 there of this review. What you see there is two lines. One is a straight line down here at around about 17% in this case of oxygen, maximum oxygen caloric consumption per unit time. 17% of your VO2 max, for those that understand a little bit about exercise physiology. That's a straight line, so this indicates that this is a person undertaking a series of rhythmic muscular contractions that have been going for enough amount of time previous to this graph that the oxygen system has caught up to the level that subserves the energy requirements. And basically we have a stable state of oxygen consumption producing energy via the mitochondria. And so if we were to integrate the area under that straight line right across the page there, that will give us an area for this rectangular shape here. And that area would be, whatever it is. What we see here in this other line is a straight line for most of the time, and then suddenly it shoots up massively, and then suddenly it massively shoots back down. Straight line again, shoots up massively, straight back down, shoots up massively, straight back down again. What we're seeing here is 3 discrete muscular contractions at roughly half a second in time each, separated, I should say, by half a second each. So that's, 3 contractions in the space of about a second and a half. And what you can see if you integrate the area under this line, so all of this stuff here, which is slightly lower than the average oxygen consumption, and then add in these spikes, the area under both those 2 curves is the same. Okay, so we've got oxygen consumption occurring, rolling along at a steady state, which subserves the needs of the energy expenditure, which for most of the time is actually below what's coming in by way of oxygen consumption, and then for very much the smaller portion of time, it's by far and away above. In fact, the energy expenditure requirements for even these 3 quite mild muscular contractions is indeed above 100% of the stored energy as ATP in the cell. So in other words, even at your exercising at around about 17% of your VO2 max, each individual muscular contraction would indeed entirely drain that cell of ATP and thus mean that it would not be capable of a second contraction were oxygen consumption not occurring. Okay? So to all intents and purposes, the answer to what our anaerobic capacity is, I'll give you the answer. There it is there. It's about 1 contraction, even at a very, very low rate of intensity. Obviously, if you increase the intensity of those spikes, in other words, we have more intense muscular contraction, then the VO2 line will come up over time to meet that. So we'll have, a stable state there. And if you truncate down the time in between the muscular contractions, same deal, the oxygen consumption will come up. Area under both those lines will remain equal. And the oxygen consumption subserves the need for energy production. Okay. And we find all this stuff out. We found it out by some people called Shulman and Rothman, who did some studies using a 31 PNMR machine, which is capable of millisecond resolution in terms of measuring the ATP expenditure and production in muscle cells. And they found out that the ATP requirement of muscular contractions is orders of magnitude higher than what they thought it was, using the old classic biochemical assays. Because of the millisecond resolution, they were missing most of it, and so that's why they couldn't pick it up. That's why they didn't understand that actually one single muscle contraction will drain the muscle cell of ATP entirely. And so there you go. That's basically how those 2 systems interact. In terms of physically, how does that work? Well, let's cover that. What I'll do is come back to the screen shot. Where are we? There we are. Hi. And basically, these 3 energy systems that we've got are, the aerobic system is in the mitochondria within your muscle cells, which are many and numerous. They will consume oxygen. They will consume reducing equivalent from your food stuff. They will produce ATP. That ATP never actually leaves those mitochondria. A lot of people say mitochondria produce ATP subserves the muscle cell. That's nonsense. They do no such thing. The ATP that is made by muscle cells remains in those muscle cells. It is hydrolyzed at the membranes of those mitochondria immediately upon its creation. And the reason that they do that is to subserve the cell's ability to produce what called phosphocreatine, that third energy system. The phosphocreatine is a spatial and temporal energy buffer between the mitochondria and the remote site of the muscle contractile machinery, which are protein strands that fit together like this. Those vast, rapid, stepwise changes in ATP requirement for those muscle contractions, they necessarily subside by ATP being generated vastly rapidly. If you think of the inertia in the aerobic system and the mitochondrial system, that rate of oxygen consumption goes along fairly steadily as a function of time. Because of the inertia, you cannot speed it up and slow it down as quickly as needs be. So we need another system, and that system that actually does fire or does fuel those muscle contractions is glycolysis. It's actually glycogenolysis. It's the splitting of glycogen or glucose starch in the muscle fibers. And that's what's usually called the anaerobic energy system. Actually, all muscle contractions at every level of intensity necessarily must be fueled by glycogenolysis. They're not fueled by the mitochondria whatsoever. So you can see that these are different gears, if you like, in a gearbox that spin off each other. You remove one, you stuff the function. Okay, so they're not discrete energy systems that one prevails or the other prevails. They all work together. You need all of the systems running. So you've got mitochondria producing ATP, which is used in mitochondria immediately to produce phosphocreatine. The phosphocreatine goes to the muscle contractile machinery. There it's split, and it's split there so that the glucose coming in from the blood to the muscle cell can be formed into glycogen. That glycogen is then split in order to subserve the ATP requirements of contraction. That produces lactate. The lactate then exits the muscle cell into the blood, goes back to the liver where it goes through the Cori cycle. It's oxidized to pyruvate, and then we can go through gluconeogenesis and make new glucose from it. So that's recycled in that fashion. That's how all the systems interact. Okay. So basically what I'm saying is there are no discrete or anaerobic energy systems that do not require you to be consuming oxygen. They all work together. Phosphocreatine is a spatial and temporal energy buffer between mitochondria and the contractile machinery in the muscle cell. Glycogenolysis is the actual fuel for muscle contractions, not mitochondria. If you remove mitochondria or you stop the mitochondria from functioning, you get one muscle contraction, then you've got permanent tetanus, you've got death. The end of story. If you remove all the glycogen from a muscle cell, it will not contract. Death. If you remove all the phosphocreatine, then the mitochondria can't communicate with the muscle contraction machinery. No muscle contraction. Death. They're all interdependent, basically, is what I'm saying. Okay. Well, that being said, the reason I'm saying it is because you need to understand that material before I launch later in the week into a discussion around why it is you should never do aerobic type exercise as I outlined at the beginning of this video. Okay, so hopefully that was useful and hopefully that was accessible, it was understandable. If it wasn't, please send me an email. I need you to understand this material so that you can understand my next video, which will explain to you the exact reasons why you should never do cardio type or long, slow distance, low intensity, continuous exercise for hours on end, like other people said. Okay, so that was the reason for this video. Stay tuned. So hopefully the quality of the videos gets better. Let me know that this one is working well, please. Thank you very much. Have a great day. See you a bit later on. Okay.